Today we are going to be answering topic 6 paper 1 questions. So the first question says hydrochloric acid is reacted with large pieces of calcium carbonate. The reaction is then repeated using calcium carbonate powder. How does this change affect the activation energy and the collision frequency? Alright, so here you have an image of the large pieces, which have a greater surface area because they are large pieces. And the powder, they're smaller particles, so they have a larger surface area. Smaller the particle, the greater surface area, and the less the volume. Alright, and it asks us to say how does this change using the powder instead of the large particles affect the activation energy and the collision frequency. So here we have the two options. When it comes to activation energy, it asks us to say whether it stays constant or increases, and when it comes to the collision frequency, it asks us to say whether it stays constant or increases. So when it comes to activation energy, there is a very, very crucial rule we need to know, and it is basically that nothing can change the activation energy other than a catalyst. The catalyst is the only thing that can change the activation energy by reducing it. So here I wrote the rule over here. It says only thing that can change the activation energy is a catalyst by reducing the activation energy. So here it does not mention a catalyst. Only change we had is using the powder instead of the large particles. So the activation energy here will stay constant. Now when it comes to the collision frequency, however, it is going to increase. Why so? It is because when we have a smaller surface area, we have more particles, more number of particles, and therefore the collision will increase. So for example, if I have the same mass or amount of calcium carbonate, but one is a large particle and here we have a powder, the powder, when it's put in a reaction, is going to have more collisions. That is because in the powder we have way more, the number of particles is more than in a large block. Alright, so when the number of particles is more, there will happen more collisions. I like to think of it exactly as if I put 100 people in a room and I tell them to run all over the place. When those 100 people run all over the place, they're going to hit each other more collisions will occur. But if I get 2 people and put them in the same room and I tell them to run all over the place, they will collide with each other way less. Okay, so the one with a lot of people symbolizes the more the particles, or when the surface area is larger and the particles are smaller in size, smaller in volume, but the surface area is larger. And that is exactly what happens when we have a powder instead of large particles. So therefore, the collision frequency will increase. Second question asked us, which statements out of these 3 explains the increase in the rate of a reaction when the temperature is increased? So here we're talking about the rate, okay? So first we need to know what happens when the temperature increases. When the temperature increases, increasing the temperature means the kinetic energy of molecules increases and they move faster, so particles collide with each other more frequently, all right? I like to think of it exactly like we said in the past room example. So if I have a room with a couple of people and I tell them to walk slowly, all right, they're going to hit each other way less because they're walking slowly, everything is slow. But if I tell them to go crazy and run all over the place, they're going to hit each other way more often because they're going all over the place and they're moving faster. That's exactly what temperature does to particles or molecules. It increases their kinetic energy, makes them go crazy and move all over the place. So when they move all over the place, they're faster and particles will collide with each other more frequently. And here we have the Boltzmann temperature curve, and it shows here the blue one is when we have low temperature and the red one is when we have higher temperature. And here is the line that shows the activation energy. And so when we have the lower temperature, we have a very small amount of particles that actually can surpass the activation energy, all right, and react. However, when you have a higher temperature, we have more particles that have more kinetic energy that can surpass or exceed the activation energy or become equal to the activation energy. So we actually have, when the temperature is higher, we have more particles that collide with each other or surpass the activation energy and therefore can react. So here we need to read those 3 and say which ones of them are true and which ones are false. First one says more particles have energy greater than the activation energy when the temperature is increased. This is completely true, as we have said here. When the temperature is higher, more number of molecules will have energy greater than or equals to the activation energy. So the first one is true. The second one says the frequency of the collisions increases. This is also true because we said they have more kinetic energy. So when they have more kinetic energy, they move faster and they collide with each other more. So the collisions increases. This is also true. Third one says the activation energy decreases. And this is completely false because we said before, nothing can change the activation energy other than a catalyst. And this question, there was no catalyst, there was no nothing. They just asked what happens to the rate of a reaction when temperature is increased. That's all they asked. So here the answer is 1 and 2. Third question asks which factors can affect the reaction rate. So we need to read it. The first one says the state of the reactants. So this is completely true because here when we have a solid, it will react at a way slower rate than we have a gas because the gas molecules are free to move and move more quickly all around. So they will collide with each other more often, and therefore the frequency of the collisions will increase and the reaction rate is going to become faster and the reaction rate will increase. So the reaction rate in a gas is way more than a reaction rate in a solid, where the particles are stiff and do not easily move around, all right? They move slowly, and therefore the reaction rate in a solid will be way slower. So the state of the reactants, of course, matters when it comes to reaction rate. So I is true. Double I, the frequency of the collisions between the particles, of course, this is also true because when particles collide with each other at a lower frequency, when particles collide with each other at a higher frequency, the reaction rate increases because the reaction is occurring. The particles are colliding together quickly. The reaction is happening more quickly. However, when they slowly collide with each other or barely collide, or the frequency of the collision between the particles decreases, their action is basically not occurring. So, or occurring at a very slow rate. So the frequency of the collisions, of course, matters. The average kinetic energy of the particles, it also matters, as we said before, in the temperature. When the temperature is higher, the average kinetic energy of the particles is higher and they move at a faster rate. All right, so I, double I, and triple I, they all matter and they all affect the rate of a reaction. And so the last question, which is actually the hardest question, it says a student added 0.2 grams of calcium carbonate powder to a volume of 100 centimeter cubed of 1 mole decimeter cubed hydrochloric acid and excess. This is crucial to know that the hydrochloric acid is an excess. And measured the volume of the gas that was evolved. The graph of the results is shown below. So here we have 0.2 grams of calcium carbonate, a volume of 100 centimeter cubed, and a concentration of 1 mole decimeter cubed. And here we have a diagram of the hydrochloric acid, which is an excess. Which graph would be obtained if 0.2 grams of calcium carbonate powder is added to 100 centimeter cubed of 0.5 mole decimeter cubed hydrochloric acid and excess? So here we have the same exact conditions, same exact reactions, except the concentration here is actually less. It's divided by 2. Here the concentration is 1 mole decimeter cubed. Here it is 0.5 mole decimeter cubed. So here we need to know something very important to help us answer this question. It says, we need to know that the excess does not affect the amount of gas produced in the reaction. Only the limiting can affect the amount of gas produced. So knowing this, we need to know if here the amount of gas produced is 50 centimeter cubed, or the volume of gas produced is 50 centimeter cubed, then the volume here will not change as well because hydrochloric is an excess, and we said the excess does not affect the amount of gas produced. So we're going to immediately eliminate C and D because the volume or the amount of gas produced in those are different and the excess does not change that. So the options we have are A and B, and we need to limit it down to one of them. Second rule we need to know is that concentration and rate are proportional. So as concentration increases, the rate of the reaction increases, and as concentration decreases, the rate of the reaction decreases as well. So knowing that, knowing that the concentration decreased here, we need to know that the rate of the reaction will decrease here as well. So which diagram, A or B, shows a decrease in the rate of a reaction? Definitely B, because here we see a slope is higher or more steep. So obviously the rate of the reaction is way faster than the original one here. But here the slope is not that steep, and therefore the rate of the reaction is slower.